In this lesson, we'll continue our discussion on big idea number 2, talking about the rate of chemical reactions and describing them quantitatively. And then we'll also touch on big idea number 2. How can you manipulate a reaction to make it go faster or slower? That takes us to learning target number 4. By the end of the lesson, you should be able to describe the factors that affect the rate of reaction and explain why each works at the molecular level. We often take for granted the fact that we can mix two reactants in a beaker and instantly see a reaction form. In order for reactants to complete a reaction and form products, the following conditions must be met. The reactant particles must collide with each other. This is known as collision theory. This is not as easy as it sounds. Remember, particles can have vibrational, rotational, and translational motion. They move randomly in three-dimensional space. They do not have consciousness. Therefore, if I react particle A and particle B together, sure, A will collide with B, but a lot of A's will hit a lot of other A's, and a lot of B's will hit a lot of other B's. So not every collision will produce a reaction. Secondly, reactants must collide in one particular way in order for the necessary bonds to form in the products. This is known as collision geometry or orientation theory. If they don't collide properly, the reactants will just bounce off of each other and no reaction will happen. Condition number 3. Reactants must collide with enough kinetic energy to break the bonds in the reactants. This is known as activation energy theory. If they don't hit at the right speed, they will just slide past each other or bounce off of each other. Now, if conditions 1 to 3 are met, reactant A and B collide at the right orientation with the right activation energy, then a highly unstable chemical species is formed with partial bonds. This is known as transition state theory. This temporary chemical is known as the activated complex, and it only has a 50% chance of falling into the products, or just back into the original reactants. So how is it that we can have reactions that we just mix two reactants together and we get a reaction? Well, we often use billions and billions of particles, because the more collisions that happen, the better the chance that a proper collision is going to occur. We can take these steps during a chemical reaction and expand on the energy diagrams that we were drawing in the beginning of the unit showing the enthalpy change. We can now include activation energy and transition state theory onto our energy graphs. Here are some examples. Because the reactants have higher energy than the products, this is an exothermic example. The difference between reactants and products is shown on the graph as being our delta H value. All we've done over our previous graphs is just move our products over to the right-hand side, and we've put time on the x-axis. When reactants collide and hit each other, they slow down, and their kinetic energy is converted into potential energy, which can be used to break bonds. This is why you see this hill. At the top is known as the transition state. This is where the activated complex exists. The energy difference between the reactants and the transition state is known as the activation energy of the forward reaction. There's a little FWD there. If your reactants collide at the right orientation and the right activation energy, they will be able to climb up this hill and reach the transition state. then the activated complex that exists here has a 50% chance of sliding down either side of the hill, going back into reactants or changing into the desired products. Now, if I really wanted to, I could make an exothermic reaction run backwards and create an endothermic one. The activation energy for going in the reverse direction would be climbing up this hill to get to the transition state. That's why the energy difference between the products and the transition state is labeled as the activation energy of the reverse reaction. Now, you do have some equations in your textbook where you could sub in values and rearrange. They would give you two of these numbers of these three values, and then you could rearrange and find the missing one. But because this is a graph, it's a scale diagram, which means that these differences here you can treat as vectors. So say, for example, I have the enthalpy change and I have the activation energy of the reverse reaction, and I'm asked to find the activation energy of the forward. All I would do is subtract this number from that number. Next door is an example of an endothermic graph. I know that because the energy of the products is greater than the energy of the reactants. That means that my system has gained energy. Let's have a look at example number 1. It tells me that substituting a chlorine onto a methanol is endothermic, and it gives me the delta H and the EA forward. It asks me to draw a potential energy diagram. Because this is an endothermic process, I know on my graph that my products will have higher energy than my reactant. To connect the two, I draw a hill higher than the products so that I get a transition state. Now the delta H is the difference in energy between the reactants and the products. As a double check, remember it's a positive delta H. That means your arrow should be going up. Now the EA forward is the difference in energy between the reactants and the transition state. Now the difference in energy from the products in the transition state, that's the EA of the reverse reaction. Now if I wanted to know the value, I would just subtract these two numbers. Now don't forget the labels on your diagram. This here is energy, and then on the x-axis we have time. Now to address the second part of the question, it asks us to suggest an appropriate activated complex. Remember, an activated complex is a mixture of the reactants bonded together with temporary bonds. Let's start off by drawing our methanol. Methanol has one carbon and it's attached to 3 hydrogens, and it has a hydroxyl functional group. And I have to substitute on a chlorine. If these two reactants collide, then I'm going to get a carbon that's got, for a very split second, more than 4 bonds. And that makes sense that that would be my activated complex, because it breaks the octet rule. So my activated complex might look something like this. where I've got my carbon and my hydroxyl functional group attached. I'm still going to have my 3 hydrogens attached, and then I'm going to have a chlorine attached on as well. Now, these bonds here are going to be the very unstable ones. If I have a chlorine colliding opposite of the hydroxyl group, it might transfer force through the molecule and knock this and throw it off. These two bonds are going to be the ones that carbon has to choose. 50% of the time, carbon will choose to break this one and make the expected products. But 50% of the time, this bond will get broken and you'll just get your reactants back again.